Okay, so we're going to talk about error bounds or error estimates. Error estimates. Okay, and a lot of times we're talking about an estimation or a bound on the error. Why? Because, well, if we're trying to estimate something, we want to know that our estimation is as close as possible. But we aren't going to know what the actual error is, because if we knew what the actual error is in our approximation, then we'd know what the original value is that we're trying to find. So we wouldn't spend time estimating it. So basically, a couple of places where this shows up is in the section on numerical integration. So in numerical integration, we often have a few different methods. So we're talking about Riemann sums. Maybe we have a left and right hand Riemann sum. We also are going to have, we can do an estimation with trapezoids. So if we have like from A to B, and then I have, in things here, I want to, for trapezoidal, I'm basically making little trapezoids and using the area under those trapezoids to approximate the area underneath the curve. So we have trapezoidal. Another way is midpoint, and so for midpoint, basically you're taking a point in the middle of each interval and you're computing the height at that interval, and you're just taking these heights, these rectangles that are the height of the midpoint. So we have the midpoint. And then the other thing that we learn in the section on numerical integration is about Simpson's rule. And so basically what Simpson's does is it makes little quadratics. So the top, instead of being flat like a trapezoid or like a flat rectangle, it's going to have a little piece of a quadratic on top, and so it's going to use those, so it's kind of curvy on top to approximate the area there. And so, but of course, every time we're doing this kind of approximation, there's going to be some amount of error. And so, so what we want to be able to do is figure out how can we make that error, within a certain range that that is acceptable. And so, if I think about trapezoidal and midpoint, so I'm going to draw kind of a curvy line there. And if I'm trying to approximate this, with a trapezoid, maybe I'll use green for trapezoidal, then I would have, this. If it's concave up, then that trapezoid is going to be an overestimate. So this amount here is the actual error for the trapezoid. So this is the actual error for our trapezoid. For midpoint, it turns out that midpoint is going to be the same as if you took a tangent line to the curve on that interval. That the error for the midpoint, it switched to erasing for some reason. The error for the midpoint is going to actually be this red area, and so the red area will be the error from the midpoint approximation. So if this is an concave up, then the midpoint is actually going to give us an over or an underestimate. Okay. So notice that the midpoint error and the error for trapezoidal are both depending on how curved the graph is. So if the graph is more curvy, then there'll be more of this green space in there. And so the midpoint and trapezoidal don't work as well when the graph is super curvy. And remember, the curvature of the graph is dependent on the second derivative. And so the trapezoidal and midpoint are both going to be bounded, or the bound is going to depend on this value of K2, which is going to be, which is a maximum. So K2 is some value that is greater than or equal to the absolute value of f double prime of x, on the interval AB. Okay, and so we want to have some bound on the second derivative, which is telling us how curvy it is, or how the concavity. And so the error bound for the midpoint within rectangles is bounded by this K2 times b minus a to the third over 24n squared. And the n is the number of rectangles. And then the error for trapezoidal is going to be bounded by the actual error will be less than or equal to this bound. It also has a K2 in it, b minus a cubed over 12 n squared. Okay. And then for Simpson's rule, the bound is given by, it's going to be similar, but it's actually going to depend on the fourth derivative. So the error for Simpson's rule is going to be less than or equal to K4 b minus a to the fifth over 180 n to the fourth. Okay, and so let's just do a quick example. I'll just do one. Let's calculate the error for this. Let's see, if we do this integral, let's do the integral from 0 to, let's do this one. The integral from 0 to 1 of e to the negative x squared dx. Okay, and so we'll calculate the error bound for this thing using, let's just do M5 or something like that. Okay, so the bound for M5 is going to be given by, I'll need to first find the K2. So if my f of x is equal to e to the minus x squared, then my f prime of x would be, I'm going to use the chain rule there. So I'll have e to the negative x squared times negative 2x. And then for f double prime, I'll have to use the product rule and chain rule. So I'll have e to the negative x squared times negative 2x times negative 2x plus e to the negative x squared, e to the negative x squared times the derivative of negative 2x, which is just negative 2. So this actually ends up being e to the negative 2 or negative x squared times, I'll have 4x squared minus 2. And so what I need to do is I need to bound that on the interval from 0 to 1. So I'll want to look at the graph of that on the interval from 0 to 1. So I'm just going to throw that into Desmos real quick. And so when I look at that graph in Desmos, it looks like this, and it looks like it has a minimum at negative 2. Okay, so it looks kind of like this, so the minimum is at negative 2. So that tells me that K2 is equal to the absolute value of that minimum. So K2 equals 2. So 2 is like a bound on the second derivative, the absolute value of the second derivative. So to do my error, it's going to be, the error is less than or equal to K2, which is 2, and then b minus a is going to be 1 minus 0, cubed over, and I'm doing it midpoint, so 24 times the number of rectangles, which is 5 here. So I'll have 5 squared. So that's going to give me 2 over 24 times 25, so whatever that is. And so that can tell me what my error, the actual error, will be less than this amount. So that tells me kind of a measure of accuracy for that. Another thing you're going to see is that it's going to ask you sometimes to find the number of rectangles for which the error is less than a certain amount. So I could say my my actual amount of error is going to be, if I wanted to figure out how to make it, accurate to, 3 decimal places or something, then I could take my 2 times 1 minus 0 cubed over 24 n squared, and I want to make that less than, maybe I want the error less than 0.0001 or something like that. Well, what I need to do is just take this and I'm going to solve it for that n. So you can kind of, flip that inequality around and keep going from there and just solve for that n. Okay, so that is error bound in terms of the estimates for integration. But error bounds show up all over. Anytime we're trying to approximate something, we want to kind of have a bound on the error. So another place where these error bounds show up is when we're doing alternating series. So think about an alternating series. Let me just go to a clean page here. All right, so for the alternating series, we can talk about the alternating series estimation theorem. So like a classic example of an alternating series might be -1 to the n over n. So this is equal to, well, the first term will be -1, and then the next term will be plus a half, minus a third, plus a fourth, minus a fifth, plus a sixth, minus a seventh, and so on. And so if I were to plot this on a graph here, I would see that I'm going to plot the partial sums. So the first partial sum would just be -1. So the first partial sum is -1. And then the second partial sum would be -1 plus a half. So if I add a half to that, so the second partial sum will be -1 plus a half. So if I add a half to that, what that means is that I'm going to go in this direction by a half, and I'm going to land right there. So this distance is 1/2, right? This distance is 1, and then that's my partial sum right there. And then the next thing I can say is I'm going to subtract from that 1/3. So I'm going to go 1/3 from here to there. I'm going to subtract off a third. And that's where my next dot is going to be. So that distance there is 1/3. Okay, and then somehow this is going to be bouncing around on either side of some limit L. Right? And so we don't know exactly what that limit is, but we know that it's going to be kind of these partial sums are going to be kind of bouncing around on either side of this limit, getting closer and closer to it, right? So the actual amount of error for this, let's just look at the second one. The actual amount of error is the distance from this red dot to that limit. So this is the actual error. And so what the alternating series estimation theorem is telling us is that the actual error for any given partial sum, so this is the error for S2, where S2 is the second partial sum. And so so when I write down this estimation theorem, the alternating series estimation theorem theorem, it says that the difference between S and Sn is less than or equal to Bn plus 1. Sorry, let me make these n's both capital. And so what is this? Okay, so that S is the actual sum. Okay, I should have used an S over here. So this S is like the actual sum. So this is the actual sum. Like if I were able to add up infinitely many of these guys, I would get that value S. Sn is the nth partial sum. So if I subtracted them and took the absolute value, that would be like how far off is my nth partial sum from the actual sum? In other words, how close am I? If I add up the first n terms, like how close is that to the actual sum if I added up infinitely many, right? And so what this is saying is that the difference between those two is going to be less than or equal to the next term. And so if you remember when we talk about alternating series, a lot of times we'll write it this way, like -1 to the n, or maybe n plus 1, bn. So this bn is like the positive, or this is like the positive part. So like ignoring the sign flip, right? And so we can see it in the picture there because, okay, so see the green is the actual error for S2. But notice that the 1/3 is going to go from that place where we are for S2, and it's going to add 1/3. It's going to go to it's going to go farther than the S. So this blue distance is going to be greater than that green distance, which is the actual error. So the actual error is represented by this green distance here, is here in the drawing, and then the Bn plus 1, that's this blue distance here. So what this is saying is that that green distance, the actual error, is going to be less than or equal to that blue distance when we go like from the S2 all the way to the next term. It's going to go past S because it's flipping back and forth each time. Okay, so how do we use the alternating series estimation theorem? Okay, so basically what we can do is we can say like, okay, say I want to compute, so I could just say S2. So I know that, say I compute S2. So S2 is going to be -1/2. So the question is, how close is that to the infinite sum S? So if I call this S, that infinite sum, well, I can say it is within 1/3 by the alternating series estimation theorem. So I can say S minus S2 is less than B sub 2 plus 1, which is equal to 1/3. And so if I want to say how far do I have to go, how many terms do I need to be accurate to within, I don't know, let's say 0.01. Okay, and so what is that? That's equal to 1/100th, right? So I want S minus Sn to be less than B sub n plus 1, which I want to be less than 1/100. Well, what is B sub n plus 1? For my particular series that I had, remember my series was this series, right? My Bn plus 1 would be 1/n plus 1. I want that to be less than 1/100. Okay, and so, well, this one's going to be pretty easy. So I can flip the sign there, or I can flip the fractions over, and I get n plus 1 is greater than 100. And then I can subtract that over. I get n is greater than 99. So if n is strictly greater than 99, I can say n equals 100. Will get me there. So if I want to get within 100 of my sum, within 1/100th of my sum, I need to go out, I need to compute 100 of those, I need to take 100 of the terms and add them together. So the 100th partial sum will be close enough. So the 100th partial sum will have error less than 0.01. Okay, so that's how you would use the alternating series estimation theorem.